Okay, now next little podcast here, we're still talking about matter and change, but what we're going to focus on is what all this matter is made up of. Whether we are talking about pure substances or we're talking about mixtures. Again, if we separate that down, if we separate our mixtures, because remember, we can take our mixtures, whether they're homogeneous or heterogeneous, and we can separate them into their pure substances, right? And let me erase that, not pure elements, pure substances. So we can take our mixtures and we can separate them into our pure substances via physical changes or physical mechanisms. So we can evaporate water off of our salt, we can filter our water and recover our sand. So those are all physical changes to take our mixtures, separate them into pure substances. Well, we can take those pure substances again and use chemical changes, right? Or chemical processes to separate them into individual elements. Now, there's lots of different ways we can do this. There's decomposition reactions, there's electrolysis, there's replacement reactions, so tons of reactions that we'll look at. But we can take mixtures, this is the important thing, we can separate them into pure substances by physical processes. If those pure substances are compounds, we can take those compounds and separate them into their individual elements with chemical changes. So since everything essentially can be broken down into elements, and obviously we can have nuclear reactions and break down our elements, but we don't really want to do that because that gets into more physicsy stuff, and we want to stay within the realm of chemistry. So we will take our elements and focus on those here in this podcast. An introduction to elements. Okay, so our elements, all of our matter is made up of elements. Our elements, all our known elements are listed on the periodic table. Obviously, we have a chapter on the periodic table, but this is just an introduction so we can read it, so we know what this means. When we take a look, first off, just the physical structure of this. Notice how this one's nicely color-coded. It's such a pretty table. Anyway, we have vertical columns, up and down. These are vertical. Vertical columns are sometimes called families. And they're called families because they have similar properties. So they have similar properties up and down. So the up and down groups, here we have an up and down group. Notice this one is gray, just like this. This is alkaline metals. Our green one is our alkaline earth metals. Everything in the middle is called a transition metal, if we look at this. So our vertical columns are families, and they all have similar properties. That's probably all we need to say about that right now. If we look horizontally, if we go across, this is a row horizontally across. So it's called a row or a period sometimes. So this is a period. I like to call it a row. It's a horizontal group. Not necessarily. So we're in, again, this might be getting a little bit more specific than we need to go right now, but they're in the same, typically they have electrons in the same energy level, but they don't necessarily have similar chemical and physical properties going across. So the similar properties are the up and down, are the vertical families. Groups going across the periods don't have similar properties. They actually change as we go across, and we'll look at some of those changes rather in depth here in chemistry. So we have families up and down. We have our families. Those have the similar properties across our groups, across our periods, but they have changing chemical and physical properties. So changing, across, similar, up and down. Okay, I think I've said that a few times. As you will notice on this periodic table, if you look at this, notice alkaline metals, alkaline earth metals, transition metals, notice other metals, notice the vast majority of stuff on our periodic table are metals. So one thing that should have right here is the zigzag line. So we consider everything to the left here a metal. And if we look at this chart, it agrees, alkaline metals, alkaline earth metals, transition metals. So these are all our metals on the periodic table. The vast majority of our elements are metals. And up here are non-metals. So they're non-metals or metals. Also, we do have some things that are touching the zigzag line. Silicon, germanium, arsenic, antimony, tellurium. That we do, and astenine, that we do consider metalloids, which means they have properties of both. So everything to the left is a metal, everything to the right is a non-metal. Things that are touching the line are considered to be metalloids. one other quick thing we want to say about the periodic table before we go into detail about metals and nonmetals is just the phase that elements are in. So notice the vast majority as well. So the vast majority of elements are metals, but also the vast majority of elements, notice these are all solids. All of this stuff is a solid. They're all solids at room temperature, which is kind of amazing, actually. The things that are orange on this periodic table, hydrogen, nitrogen, oxygen, fluorine, chlorine, argon, all of these things are gases at room temperature. And notice only 2 elements, mercury and bromine. And bromine is kind of is barely a liquid because it goes into the vaporous phase very, very easily at room temperature. It's very volatile, we would say. There's only 2 liquids on the periodic table. So, it's just kind of interesting to know. So we might like to think of metals when we think about metals in our heads being the really fancy stuff, the gold and silver and platinum and palladium. But again, really metals can be anything to the left of that zigzag line. So they can be sodium and potassium. And really what we'll see is they do all have very similar chemical and physical properties. There are some generalities we can make about all metals. And so here's a quick, easy chart just to look at the properties of metals. So notice again, metals to the left, nonmetals over there. Notice they do have hydrogen here. Hydrogen is always kind of a trick because hydrogen is a nonmetal. Obviously, it's a gas at room temperature. What they theorize, though, is if you cool down hydrogen to the point where it's a solid, that it would behave as a metal. Now, that's a theoretical idea. We generally consider hydrogen as a nonmetal, and typically they don't list it over here on most periodic tables. Well, sometimes they do, just because it fits in nice, but sometimes they list it in the middle. Sometimes they even list it over in this spot. Hydrogen, because it's so small, just doesn't really fit in very nice anywhere. Anyway, metals, if we look at their properties, all metals have luster. So that was like our picture we just had of gold and silver. They're shiny. So luster, code word, shiny. Okay, that's our word for shiny. So they have luster. We're just going to use scientific words so that we sound smarter. Okay, that's all. We don't use shiny because shiny doesn't sound like we're smart. If we use luster, it sounds like we're just slightly more intelligent. So that's what we'll do. They're also malleable and ductile, which means they're bendy. Most metals, especially pure metals, are very, very malleable, which means they can be bent. Ductile means they can be pulled into wires. So malleable, ductile really means they're bendy. But they're not bendy. They're malleable and ductile is what we like to use. Metals conduct heat and electricity. That's something I believe we already know. And here's one thing we'll put in as far as the chemistry of them. They tend to lose electrons, okay? If we look at nonmetals on the other side, they are going to have the exact opposite traits. So our nonmetals on the other side, they are not shiny. They're dull. They're not malleable. We can't make them into sheets or make them into wires like we can pure metals. They're brittle. They don't conduct heat and electricity very well, and they tend to gain electrons. So it's very interesting that we see these properties almost completely reversed when we look at our metals versus our nonmetals. So just look at some images here of our metals, and notice some of these are metal alloys, but they're still shiny. And even if they don't look really shiny, it's really just because they've oxidized it so easily they react with the air. Notice even our alkaline metals are shiny. Notice they're gray, they're shiny, they're still malleable, they still conduct electricity, just like our aluminum or our copper that's up here. But notice these have to be stored under oil because they're so reactive. They'll react with the air right away. They'll oxidize, or even worse with water. Some of them will burst into flames. So those are stored under oil, but still they're metals. They still have the same properties as metals. Our nonmetals over here, sulfur, bromine, a really bad picture of bromine. I think that's just a computer-generated image of bromine. Bromine is a liquid, but it's so volatile it'll go into the gaseous phase if you store it in a bottle, or if you open that bottle up, then the gas will escape. Sulfur can be a powder or kind of a crystal when you find it pure. But again, these are pure elements. So shiny, not shiny, right? Metals, non-metals. Very easy. Okay, if we just spend 1 minute maybe here on our metalloids, don't need to know a lot right now besides just identify where they are. Notice anything that's touching that zigzag line. Notice we exempt aluminum, which acts as a metal, and polonium down here, which acts as a metal. But anything else that's touching the zigzag line has properties of metals and properties of nonmetals. Notice there's a picture of silicon. It's metallic luster, so it's nice and shiny, but at the same time, it's actually fairly brittle. So mainly when we look at metalloids, they're mainly used in the semiconductor industry. So we want things that are not super conductive, but semi-conductive, and so our metalloids work well in that process. So lastly, here we have our noble gases. Noble gases are really pretty to look at here, but our noble gases, actually, from a chemistry standpoint, they don't do much for us, because noble gases are very stable. They're gases, and they're stable. Thus, are noble. They're unreactive, so they're noble, because nobles generally don't do anything. So they're very stable gases. Tend not to find them in many compounds, if any. That's about it. They're at the end of the row. They're stable. They're gases at room temperature. The only group that's all gases at room temperature: helium, neon, argon, krypton, xenon, radon. And we'll talk about why they're noble gases electronically in a little bit. They have all the electrons they need, so they tend not to gain or lose electrons. Kind of like we talked about, our non-metals like to gain electrons and our metals like to lose electrons. Well, these like to do nothing. Interesting side note here is they do have properties of that when we heat them up. They do emit some light here. And notice neon right here in the middle. Neon actually emits a reddish-orange light, but that's the only color light it emits. So when you're looking at the neon lights on the bars around town, only the red is actually neon gas. If you see other colors, they're actually made by other gases, some of which could be noble gases, but they don't necessarily have to be. Other gases are used in our neon lights that we like to stare at sometimes. Okay, so anyway, that is our matter and change, focusing on a little introduction to B elements.